Right, welcome back. What we finished off was with the concept of the acids and bases and all of that. But in essence, what we had there was we had the proton being given away, so to speak. If you remember, we had the hydrogen proton stuck itself onto NH3 to form NH4. We found that it went across to join the H2O to make an H3O. Okay, hydronium, oxonium ions, things like that. And then the conjugate went off and did its thing on the side. Now, the other side of all this is the electron side. What we're going to look at today is we're going to look at, I think, probably the most difficult part, I would guess, is where we start talking about oxidation and reduction reactions. I know you've seen them before, you've heard of them before. We're going to tackle them now in a slightly more rigorous manner. We're going to be talking about things like oxidation numbers, and we're going to be looking at things like half reactions, building up towards electrochemistry in the future. And in the future, the electrochemistry situation is where we, for example, where we gold plate things or copper plate stuff, where we use the processes of oxidation and reduction for an economic benefit, let's put it that way. So it's a very important part of chemistry and a very important part of everyday life, essentially, okay, because there are many of this kind of reactions. Let's just start off with a very, very basic equation. Okay, I'm going to go through this fairly slowly and fairly conscientiously, but you know, the essence once again is that for you is the best thing is to go through it with me. You know, make the notes and extract the information from it. As I say, like normal, I'm going to give the recipes and things like that, but it really is important that you actually interact on this and take down what I'm doing. Put in your own explanations, your own notes, okay, of how things in your own words. I find that's by far the best, because what it's doing is it's letting you write it in your own words that you'll then understand, even if it's your own form of shorthand, okay? So let's have a look at a very simple reaction, shall we? Let's look at magnesium burning in oxygen, shall we? Let's have a look. So what do we have here? We have magnesium solid plus O2 gas, magnesium, and we're going to burn it in air, and we know that this forms Mg magnesium oxide, okay, and let's balance this. We've got to have a 2 there, and let's put in our 2 there. Right, so now what we've got here is we've got magnesium and oxygen are changing. They are forming a compound, okay? Now, we go back and remember the valencies, those way back in the distant past? The valencies come back into this because you would say, right, I know that Mg is a +2. I'd look on my periodic table and I see Mg is a +2 and I see O is a -2. Therefore, the 2 plus is donated across to the O and the 2 can form, right. Now, then we would look at the difference in electronegativities to see if this was ionic or if it was covalent, right? Now, let's take a slightly different view. Let's ask how did this happen? What happened to the magnesium to change and allow it to become a compound with oxygen? What happened to the O2 gas? Because all of a sudden, if we look, and I kind of like to draw down here a little double line like that, just for my own sort of benefit, because that essentially is the wall, right? That's where everything is happening. That's where we've got our processes taking place, right? So what is happening at this point? Well, we say to ourselves, first of all, right, let's go back to black here. First of all, we've got a situation where the Mg was a solid and something happened to it. We had the O2 was a gas. It's now stuck onto the Mg. So what did the Mg and the O2 do in order to be able to combine? The Mg must have changed form to have linked in with the oxygen, right? Because it was happy on its own. Then we applied the heat to it, and the next thing, it joined up with the oxygen to form MgO. What did Mg actually do in this situation? Mg essentially changed to an ion, didn't it? What did we have? We had Mg changing to an ion, right? The Mg over here said to itself, okay, I'm going to become a +2 because I know that I'm going to be bonding. We know that the magnesium linked with the oxygen. That's the product. That's what happened. We have to say, therefore the magnesium must have changed. It did change. It became an ion to allow it to bond with the oxygen. Well, that's fine. But now if we go back and we look at Mg, okay, I'm not going to go through the whole thing. But remember we had Mg, and if we look at it, it had, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's number 12. So we had 1s2, 2s2, 2p6, okay? That gives us 10, 3s2. So in the outer valency structure, remember we only draw the outer ones, we had these two here, correct? So those two, then, those are 2 electrons. In order to form the ion, those 2 electrons, let's just do it, what did we do? We removed them because we gave them to, in this case, the oxygen, but we gave them away to become the ion, didn't we? So if I remove those 2 electrons there at the 3s orbital level, those 2 are gone, which means I've got more protons, so I'm a +2. That's where it comes from. If you remember some of our first sort of sessions together, that's where it comes from. So what do? We've now got that. So now we've got to account for them. So let's say, okay, so I'm going to put the 2 electrons in there, okay, because they're there, okay. So the magnesium, now, what happened to the oxygen? Well, the oxygen went to O. And we know the valency of the oxygen is -2. But now remember, over here, there was an O2, which means an O, remember, back to our molecules, double bond, that's an equal sign, but it's a double bond with the O, right? So what happened is the oxygen, we had 2 of these guys over here at the wall, remember, or at the membrane, call it what you like, at that point where we've got the activation energy and we've got the activated complex line. This is the activated complex. I like to think of it that way. On this side, therefore, we had 2 of these oxygens split up and went through the wall, and we had another O-2 over there. Okay? That's quite simple and straightforward. Now, there we've got our 2, but hold on. How did O become a -2? Right? What had to happen? It had to have got electrons, didn't it? Right? It had to have got electrons where from? Well, over here. Remember? We said, hang on, you've got 2 electrons, correct? So what is actually happening over here then? Okay? The O2 is giving us, because we've got 2 of those, each one of those O's is giving us an electron, 2 electrons. Right? Let's just go through that again. Okay? What have we got here? We've got an O and an O. Right? This O went over there and became O-2. How did it do that? It must have taken 2 electrons. This O became that one. So it too, whoops, look what I did. Call that a positive. Okay? 2 electrons over there as well. There's where the positive. So each one of the atoms, the O atoms, the diatomic O2, broke down into O and O. Then that O, okay, gained 2 electrons. Where did the electrons come from? Well, they came from the other side of the equation, from the magnesium. I haven't yet balanced this magnesium because I need to bring the balancing number down. In this case, is there, right? So I'm going to multiply through by 2, 2, and then this becomes, change it to 4 electrons. All right? Now can you see what has happened? The electrons are balancing. Now the premise of these oxidation reduction reactions is quite simply that what happens with the electrons has got to be equal on both sides. We cannot have a reaction at this point where we've got electrons doing their own thing. Okay? Because electrons don't do that. Schizophrenic, they may well be, but they don't do that. They don't hang around in soups waiting to be taken here, there, or put onto this one or that one. In these equations where we're talking about the oxidation reduction, the electrons must balance. Why? Because 4 electrons get given off one side, the opposite side takes those 4 electrons, right, and uses them to become the ion. So, what has happened here then is we say, okay, this oxygen has changed to that. Now you can see that what we've got is we've got a chemical equation. We can say to ourselves, look at this, let's put it back together. 2Mg, okay, and on this side, to 2Mg plus 2 plus 4 electrons over there, and on this side over here, I've got plus 4 electrons plus O2 gas over there. I just want to remove this guy here, all right, 2Mg plus 2O minus 2s, okay? All I've done is I've just added equation 1 and equation 2 together, all right? So essentially equation 1 and equation 2. I've just put them together. Look at what happens now. We've got a factor on this side that's going to cancel out the electrons, because if I subtract them this side, they come off that side, and there's our balanced equation. We just have to tidy up this little bit at the bottom. 2Mg plus 2s, 2, each one joins. In other words, an Mg and an O, an Mg and an O, to form 2 MgOs. Okay? And you can see that that's a balanced chemical equation. Now we need to do a little bit of, looking at actually the, let's say the wording of how we're going to deal with this. Because first of all, you saw that what we had there is we had 2 halves of the reaction. So it was split, okay? And we split it into half reactions, right? One half did one thing, the other half did something different, right? Let's look at what the one half of the reaction did and look what was different in the other part. So let us look and go back up to our table here. Let us look at, for example, this equation 1, which is the magnesium. Have a look at the magnesium. The magnesium went through the wall, okay, activated complex, and there was electrons that were sitting on that side. Okay. This side, there were electrons, balanced electrons, on the oxygen side, right? So that electrons from the one side balanced onto the other side. That's what gives us the 2 half reactions that when we add together, we get one single reaction line. Well, somebody in this process, right? Remember we started off talking about in acids and bases there was a proton donor? Well, here we've got an electron transfer. It's not called a donating rather than donating. We've got an electron transfer, right? What happened? Let's just look back at those half reactions again, shall we? Essentially, let's take the balancing number out. Mg, the solid, change to Mg plus 2 electrons, okay? So what's happening, it's actually, if you like, in a way, we could say that this magnesium melted. Now, I know that's not technically correct, but it was a solid and it's now become something else, an ion, fair enough. So it kind of changed its state, didn't it? Okay? So I sort of say to people, you know what? Look at it as the one's melting and the other one's doing something else, right? So in this sense here, all right, it changed to an ion, right? The oxygen, the O2, if you remember, okay, on this side, all right, I just want to put in my electrons here, 2 O minus 2s, okay? Let's just have a look here and say, but hold on, the O2 actually gained electrons, didn't it? So the one side lost and the one side gained, right? Now, definition, all right, you may or may not have heard of oil rig. It's just a cool way of remembering it, oil and rig. Okay, oxidation is loss. Oxidation is loss. Reduction is gain. Okay, so the one that loses electrons, okay, that's our oxidation side. So you can see that by putting them together, we've got an oxidation and a reduction, hence the redox situation, the redox name that we've given it. So yes, we have to remember that, and that's just a bit of practice. And I promise you, it comes. Just remember oil rig. Oxidation is loss, and rig reduction is gain. Okay, that's the best way to work these through mentally. Now, this process of change, okay, is invoking or using electrons, right? Let's have a look at a different setup here. We're now going to look at something, all right? We're going to introduce the concept and we're going to start working with a concept of an oxidation number, okay? Now, I know, well, I don't know for sure, but there are some of you who might not be doing this, and there are some that are, right? In essence, it's not a very difficult thing to do, all right? What we do in order to work out if it's an oxidation-reduction reaction, because not all of them are, what do? We're going to assign a number to each individual atom, element within an equation or a reaction. We're going to assign a number. That number is going to be called an oxidation number. In essence, we're looking at the terms that are used as the electron richness and so forth and so forth. But really, at the end of the day, we're going to be looking to find out, does the oxidation number change? Does it go up? Does it go down? Because that tells us what has happened to that particular atom, element within the chemical reaction. And it will show us if something has oxidized or been reduced, okay? Please, I know in the terminology you're going to see words like oxidizing agent, reducing agent. Let's just leave that for the moment until we are absolutely 100% fully understanding the concept of the oxidation and reduction side, because they can get quite confusing, all right? It's just once again part of the language, but it does get confusing. So these oxidation numbers we talk about, right? Firstly, there's a few rules that we have to apply for oxidation numbers. The first rule is we say an element has got an oxidation number of 0. So let's just say rules. Okay. 1. The element has an oxidation number equal to 0. Right, rule number 2. What does that mean? It means when we saw the oxygen or we saw the magnesium or any of those, we assign that a 0. You'll see it in a few moments in the examples that we're going to do. Then the charge on an ion Okay? The charge on an ion is the oxidation number. Okay? And for a neutral formula, compound, the sum of the oxidation numbers is equal to 0 because it doesn't have a charge on it. Okay? It sounds way more difficult than it is. Okay? A couple of these and really you get your hand in very quickly with this because it's just practice of applying these rules. That's all. And once you've done a few, the rules stick. They're not very, very complex, right? So we're saying the element has got an oxidation number of 0. The charge on an ion is the oxidation number, okay? And for a neutral compound, the sum of the oxidation numbers is 0, all right? Well, what does that mean? Let's have a look, for example, at, let's have a look at if we had, for example, lithium, okay? Lithium, we would give an oxidation number of 0. It is an 0 oxidation number because it is an element on the table. What does it mean? It means it actually has no charge, all right? Which we know because everything on the periodic table doesn't have a charge. That's the precept of how it was built up, isn't it? Number of protons, number of electrons, right? For each one, they're balanced out nicely. So that's logical if you think about it. We're just saying it's got no charge. Okay, so then what if lithium is now an ion? Remember, the lithium, okay, is in the first, so it's a +1, so it becomes a +1 electron gets given away to, I don't know, oxygen, fluorine, chlorine, whatever, okay, sulfur maybe. So can you see that what has happened is become an ion? So its oxidation number has now changed to a +1. We write it on top of it, right? So the lithium solid became an ion and its oxidation number has changed. It changed from a 0 to a +1. Okay? So that's logical. Therefore, we've said the charge on an ion is the oxidation number. Well, yeah. Because what are we doing? We're saying whether it's got electrons or not, the richness. Okay? Let's have a look at another one. All right. Let's take Na2O. Okay? Let's look at Na, right? Which is going to be, all right. Now we know that this here is made up of Na plus, 2 of those, plus O minus 2. We're going to go through the equation of forming that, right? But we know that those form ionically, okay? Now, let's have a look and see, well, there's also bonds that are not ionic, right? How do we essentially approach this? We always put down the most electronegative, okay, of the elements. And we assume that that's the one that's going to have the negative charge, and we take it to its ion state. So if, for example, we had, let us say, chlorine has formed with something, all right, we would then say, I'm just going to put let's put in silver. Okay? So we know that silver and chlorine have got together. For example, sodium or chlorine. Actually, let's rather use magnesium. Right? Let's rather use magnesium. All right? Magnesium and chlorine have got together. Now, magnesium is a +2, isn't it? Chlorine is a -1. So we know that we've got a 2 there, MgCl2, correct? Happy with that? What does it mean? We say, okay, fine. That was formed, how? Like this. Okay, I'm just writing it the wrong way around, which Do you know what? Let me write it correctly. It just makes a lot more sense if I do it that way. We say that magnesium, solid, plus chlorine, gas, goes to MgCl2. Okay. Now what did we say? We said, okie dokie. Well, let's put in an oxidation number for you. Your oxidation number is 0 because why? Well, you're an element. Cl2, let's put you in as an oxidation number 0. Now let's have a look what happens on the other side, on the product side, shall we? This one is a little bit longer than other sessions, but I just want to go through it carefully. What happens on the product side? Well, let's look. What did we say? The most electronegative is that one, isn't it? What happened here? This electronegativity, that's the one we say stays negative, so that must form a Cl- ion, correct? So therefore, let's go up top and say, how many of them? We've got 2. So we've got 2 minuses there, correct? Therefore, magnesium must have been a +2 to balance out that, because it must equal 0. Remember, we said for a neutral compound, in other words, it's not an ion, it's not polyatomic ion, it's a neutral compound, the sum of the oxidation numbers must be 0. I know these are looking like valencies right now, but when we start getting to different ions, polyatomics, things like permanganates and stuff, they're going, and chromates, dichromates, that's where we're going to find some very large different numbers that we're not used to. So what has happened here? Well, hang on, let's have a look here. Can you see that the chlorine was 0 and it went to a -2? And what happened with the red? The magnesium went to a +2. So we had 0 to +2 there, and for the green side we had 0 to -2. Okay. What has happened is that the oxidation number has changed, right? The one oxidation number has increased and the other one has decreased, hasn't it? Well, this one has decreased. It's gone from 0 to -2. And the red side, the magnesium side, has increased. Okay? Well, we can say something very interesting about that. We say to ourselves, right, we're going to say that we've seen an increase is oxidation. So if it increases, we've had oxidation. How could it have increased? It gave electrons away, didn't it? Right? It lost. Okay? So oxidation, and the opposite side of that one is the green side where we decreased, which is reduction. Why? Because this one went more negative. It gained electrons. I mean, how do you go more negative? You gain electrons. That's what makes us more negative, isn't it? In the chemical sense of the word, right? So the oxidation number is telling us what happened. It's showing us which one was oxidized and which one reduced. Okay? In the next section, I'm going to just go a little more into this. We're going to do some more examples where we're going to look at the oxidation numbers and work them out, right? Just doing a few examples up to the polyatomic ions. Then the last section is where I'm going to go and we're going to look at half reactions, balancing them out, putting them together, what we do in aqueous mediums, what we do in acidic, and what we do in alkaline situations, what we use to balance. Because what we're doing is we're going to be building up half reactions. These half reactions, okay, will tell us which one is the oxidation, which one is the reduction. The other part of it, we add them together, balance the electrons out, and that gives us our eventual final reaction, as long as it is an oxidation reduction reaction. So straight after we'll go into that and we'll do some examples. So I have a worksheet ready and we'll be able to take them down and we'll go through them slowly, assigning the numbers and then looking at which way is which. And you'll see that there's a pattern that we're going to use. We're going to start off here, we're going to go through it that way.